Welcome to today's Explainer. We are tackling one of the absolute greatest engineering challenges of our modern age: how brilliant engineers are outsmarting extreme weather to bring high-speed internet to the most remote places on Earth. We're going to dive deep into some groundbreaking research on HAPS, hybrid FSO, and RF communication.
Okay, be honest. Ever had your signal drop the exact second it starts pouring rain? Yeah, we've all been there. You're watching a video or you're on a really crucial call, the skies open up, and suddenly, nothing. Connection lost. It's incredibly frustrating. But now I want you to imagine that dropped connection isn't just a minor inconvenience. Imagine it's a disaster recovery operation, or maybe a remote island that is completely cut off from the rest of the world because of a massive storm. The stakes of providing reliable communication in remote, weather-beaten areas are literally life and death.
All right, let's dive into this. Here is our roadmap for today. We'll start with number 1, the weather problem. Then 2, meet HAPS, the sky relay. 3, FSO and RF explained. 4, the hybrid solution. And finally, 5, proving success.
Starting off with Section 1, the weather problem, when nature blocks the signal. To really wrap our heads around this problem, researchers focused heavily on Malaysia. It's a country with an incredibly diverse and, honestly, a very challenging geography. You've got deep, mountainous regions physically blocking signals, plus remote islands that completely lack any traditional ground infrastructure. But you know what the biggest hurdle is? The atmosphere itself. Heavy rain, thick fog, and even snow at high altitudes cause what's called signal attenuation. Basically, the weather is eating your data before it ever reaches its destination. Traditional satellites just really struggle to push a clean signal through that kind of atmospheric soup. That brings us to Section 2, meet HAPS, the sky relay. So to bypass those failing ground towers, we need a totally new kind of middleman. Enter HAPS, or high-altitude platform stations. Think of massive unmanned platforms. We're talking highly specialized balloons, airships, or even solar-powered drones. Unlike a commercial airplane that has to land every day, these platforms are designed to just stay aloft in the sky for weeks or even months at a time. They act as a direct communication relay, providing this crucial bridge between the satellites way out in space and the ground stations down here on Earth. And the best part? They're way cheaper and incredibly faster to deploy than launching a rocket.
And this brilliantly illustrates why HAPS is such a game changer. It is all about altitude. Down at 0 kilometers, we have our standard ground stations. Way up at 1,000 to 2,000 kilometers, you have low Earth orbit satellites. And a staggering 36,000 kilometers out, that's where your geostationary satellites live. I mean, that is a massive distance for a fragile signal to travel. But HAPS, it sits right in the stratosphere, at just 17 to 22 kilometers up. It perfectly occupies this sweet spot right above commercial airspace, completely bypassing the limitations of space-based satellites to give us a much stronger, much closer signal. Moving right along to Section 3, FSO and RF explained, the two technologies making this happen. Right, so now we've got our platform floating 20 kilometers up in the sky. But how does it actually talk to the ground? Well, first, we have free space optics, or FSO. FSO transmits data using highly focused laser beams. You can think of FSO as a high-end sports car. It offers ultra-fast speeds, incredibly low latency, and just massive bandwidth. It is absolutely amazing when the road is clear. But, just like a sports car hitting a patch of deep mud, FSO completely spins out when it hits thick fog, heavy rain, or atmospheric turbulence. The laser just gets scattered.
Next up, we have radio frequency, or RF, which transmits data using electromagnetic waves. If FSO is the flashy sports car, RF is your rugged, four-wheel drive off-roader. It has a lower capacity and lower bandwidths, so, it's not going to win any speed races. However, it is incredibly reliable. By using carefully calculated frequencies, RF can push a solid connection right through that heavy storm or dense fog.
So, looking at them side by side, it's quite the contrast. FSO gives you huge capacity and zero lag, but it's hypersensitive to the weather. RF gives you lower capacity, but it's tough as nails and weather resistant. Researchers quickly realized that neither of these technologies is perfectly equipped on its own to solve the Malaysia weather problem. If you only use FSO, your network crashes every single time it rains, but if you only use RF, you just can't provide modern 5G speeds.
Which brings us to Section 4, the hybrid power solution.
This is where we see a stroke of sheer engineering genius. The solution combined these two distinct technologies into one dynamic, unstoppable system. Here's how it works. Step 1.
The weather is perfectly clear, so the system uses the FSO laser as the primary channel. You get blazing fast 5G speeds. Step 2, a sudden monsoon rolls in. Severe weather attenuates the laser beam, and the signal starts to drop. Step 3, instantly, the system detects this and seamlessly switches over to the RF backup channel. Your internet speed might drop slightly, sure, but the connection never breaks. The data packet actually survives the storm.
Waqas Javed, the author behind this research, really hit the nail on the head here. He notes the hybrid system overcomes the limitations of each technology and provides a reliable and efficient communication system. By pairing the sports car with the off-road vehicle, engineers have successfully created a system that delivers the absolute best of both worlds. It is a massive victory for remote connectivity.
Finally, let's look at Section 5, proving success through simulation. Now, what's really interesting here is how they prove it. Because before spending millions of dollars to launch these high-altitude platforms, researchers have to validate the theory. To do this, they use powerful software called MATLAB to simulate real-world physics using some pretty complex mathematics. They feed it key formulas. They use link budget to calculate power over distance. They use the Shannon-Hartley channel capacity theorem to figure out the absolute maximum data rate. And crucially, they track the bit error rate, or BER, to see exactly how much data gets corrupted by the virtual weather. They are simulating factors like signal-to-noise ratio and atmospheric attenuation long before a single balloon ever leaves the ground.
And the math absolutely checks out. When comparing the bit error rate, a clear channel obviously has incredibly low errors. But when they introduce heavy atmospheric turbulence into the simulation, which they call a gamma-gamma pointing error channel, errors naturally spike. However, the simulation proves that because of the hybrid FSO and RF switching, the system successfully mitigates this turbulence. It actively keeps the data flowing with a completely acceptable error rate, even when the virtual weather is at its worst.
So, what is the big takeaway here? Why does all this complex math and high-altitude tech actually matter to us? Because it's literally the foundation for the future of global communication. We're talking about expanding 5G and whatever comes beyond 5G to places that have never even had broadband. It means during a massive earthquake or a tsunami, when ground towers are completely wiped out, disaster recovery teams can just deploy a HAPS platform and instantly have reliable, high-speed communication. It's vital for secure military operations, and it is the absolute key to rural broadband expansion. It's the difference between a buffering emergency feed and a seamless, life-saving data stream during a total blizzard.
So I'll leave you with this thought. How will high-altitude hybrid networks redefine global equality by bringing 5G to the most unreachable corners of the Earth? By combining lasers, radio waves, and stratospheric balloons, it seems we might finally erase the digital divide for good. The weather is no longer an insurmountable barrier. I really hope this deep dive sparked your curiosity about the incredible engineering happening right above our heads. Thank you so much for joining me for this explainer, and I encourage you to keep exploring the amazing world of global connectivity.